in the last video, we talked about how humans over time have gotten better and better at getting more calories out of a given unit of land. And one thing I do want to emphasize, in the last video, these numbers that I came up with, I picked these numbers to make the math fairly simple and to give you the general idea. I don't want you to think that the most that a square kilometer can support today is exactly 1,000 people. It depends hugely on what the land is like, how much of the land you're actually using for agriculture, what crops you're planting, etc., etc., how the people are living, how many calories they need. The whole point of the last video was just to give you a framework that, wow, there is this upper bound based on how much productivity you actually get from the land. Now, what we want to think about in this video, that was kind of, the last video was this axis right here, getting more and more out of the land. What I want to think about in this video is how did humans, through different technologies, how did we get by doing less and less of the labor for getting those calories out of the land? Obviously, you just don't have land and things spontaneously grow. Well, I guess that would happen in the wild. But if you're doing agriculture, you need to put some energy into the land. You gotta work the land. And so what we have over here in this chart, and this chart is derived from information from this book right over here. This is Energy and Society. And what we want to think about here is the different ways that humans have gone about to till soil. So we're not even going to think about the total process or the total energy required to grow a certain crop. What we're just going to focus is one step of the agricultural process, and that is tilling the soil. And in case you're like me and you have never worked on a farm, which that's one thing I would like to change one day, is actually go through that process. But tilling the soil is kind of churning it up. So you get the nutrients from the bottom layers to the surface. You dig, you bury all of the remains from the last harvest. You bury all of the weeds so that they die, and you also kind of get air in the soil. What it does is essentially it prepares the soil for the next agricultural cycle. So it's a process that humans have been doing since antiquity. And what I want to do in this video is think about the different ways to do it and how much energy is required to do it. And we're going to think about the energy in two ways. How much of that energy comes from humans, and how much of that energy comes from things other than humans. So just as an example, when we talk about human power, we're talking about someone literally hand plowing this field. So this woman right over here is literally, she has this little cart that's digging up the soil behind her. When we talk about oxen power, we're talking about the oxen doing most of the work. They're the ones dragging this plow, which is digging up all of the soil, and this gentleman has to kind of be there to supervise. But this still is fairly intense labor that this gentleman is doing right over here. And then when we talk about tractors, we're talking about a scenario like this, where the tractor is doing most of the work of actually digging up, dragging this plow behind it and digging up all of the soil. And from this book right over here, that's where we got these numbers. I'll tell you which numbers I got from them and which numbers I kind of reasoned through, because I wasn't fully comfortable with the numbers that they had. But these are their numbers. That if you're human power to till 1 hectare of soil, it'll take 400 hours. Oxen power, and this should be a pair, not a parry. That should be a pair of oxen. 65 hours. A 6 horsepower tractor, 25 hours. A 50 horsepower tractor, 4 hours. And in case y'all are wondering, what is a hectare of soil? It is literally a plot of land. A hectare of soil. Let me write it. A hectare of land, I should say, is a plot of land that is 100 meters by 100 meters. And it's roughly equal to 2.5 acres. Not exactly 2.5 acres. It's like 2.4, I think 2.47 something, but roughly 2.5 acres. So we're just thinking about how many hours to essentially dig up all of the soil for a plot of land 100 by 100 meters. So what we have over here, so clearly human takes a lot longer. Oxen, they can do a little bit faster. 6 horsepower tractor, even faster. 50 horsepower tractor, very powerful tractor, even faster than that. Now this column right over here is the amount of energy required to actually produce and maintain the machinery used. So this is a very unintuitive thing. Whenever you think about, like for example, whenever you think about the amount of energy to to plow this land over here, you tend to think, okay, well, this individual is going to have to expend a lot of her energy. You don't think about the amount of energy required to actually maintain the tool. To one, build the tool that she's using, in this case a hand plow, and then to maintain that as she does it. And so this estimate, and I got these two from these fellows right over here, or actually one of them might be a gal, but it's about 6,000 kilocalories. And this is kilocalories for lowercase c. And one thing I want to emphasize here, 1 kcal is the same thing as 1 calorie with a capital C, which is the same thing as 1,000 calories with a lowercase c. And we talked about this in the last video, but when people talk about food calories, they're really talking about a calorie with a capital C, or you could say they're talking about kilocalories. So your candy bar, 200 calories, they're talking about this right over here. In chemistry class, when you talk about the amount of energy to raise a gram of water 1 degree Celsius, you were talking about these calories here. So in all of these numbers in this chart right over here, they are in you can either view them as this unit, kcals, kilocalories, or calories with a capital C. They're essentially the same units that we used in the last video. And these are the same numbers that you were used to from a kind of a dietary calorie point of view. So for example, 6,000 calories, that's about how much a typical male would expend in 3 days. So this is to maintain it over the course of these 400 hours in the case of the hand plow. And the total amount of calories the total amount of calories that were needed to make the plow divided by the total number of hours. So whatever fraction of the plow's life is being used here, you use that fraction right over here to put this 6,000 calories. But needless to say, for at least the plow, for the kind of either the human or the oxen scenario, this isn't a significant amount of the total calories. So obviously, if you're doing it either with human power or oxen power, you're not using any gasoline, you're not using any petroleum. In all of these scenarios, we're going to assume that someone has 10 working hours in the day. And that right over here, where this is kind of a measure of how hard that person's work is. And I kind of estimated these numbers here. They're slightly different than what the original numbers were in this book right over here. But we're saying, look, if you are actually walking along using this hand plow, that is actually very, very vigorous activity. So it is going to require about 400 calories per hour to do this type of activity. You do it over 10 hours, it's going to require 4,000 calories just to do that over 10 hours. And then we're assuming that there's some rest, that the rest of the day you're going to walk around, and maybe you're going to cook dinner, eat breakfast, you're going to sleep some of it. We're assuming that the other 14 hours of the day are going to be at about 100 calories per hour. And so this is the total. If someone were to, using this technique, work for a total of 10 hours, this is how many calories they would consume in the day. And you can see this is the most labor intensive, so it looks like that they would consume the most calories per day. These two are the least labor intensive. You're sitting on a tractor, although that still requires more calories than sleeping or watching TV. And so that's the number of calories they would consume. Now this right over here, and this is the interesting number, or one of the really interesting numbers, based on all of these assumptions, this is the total human input in calories to do this task, to till this 1 hectare of soil. So over here, you're using 5,400 calories a day. If you're working 10 hours per day and it requires 400 total hours, you're going to be working 40 days, right? 400 divided by 10. 40 days times 5,400 calories per day. It's going to take a human, just the human part, not even thinking about the 6,000 calories necessary to maintain and make that plow. The human is going to spend 216,000 calories to plow that 1 hectare of land. And if you add the other 6,000 in for the actual plow, and you can debate what this number should be, but it's not a significant number compared to this, you get about 222,000 total calories. When you go to the oxen situation, you're requiring fewer hours, and each hour it requires a little less calories. This is still labor intensive, but not as labor intensive as what this woman right over here is doing. So on a daily basis, you're using a little bit fewer calories, but since you're only doing 6.5 days of this, 65 hours divided by 10, you've significantly reduced the number of calories, the total number of calories that the human needs to put into this task. Now, there still is other energy being done. Now all of a sudden the oxen have gotten involved. And if you assume that each oxen consumes about 20,000 calories a day, and you have 2 of them, so 40,000 calories per day for just to feed the oxen, and you're going to do that for 6.5 days, 65 divided by 10, the oxen are going to consume 260,000 calories to do this task. So the total energy input here now has gone up. So this is an interesting phenomenon that is going on right over here. What the human is putting in as we get better and better technology goes down substantially, 216,000 to 33,000, and we'll see with the tractor it goes down even more. But the total energy, if you include the amount of energy that the oxen have to put in, or if you include the amount of energy due to the gasoline that has to be used for the tractor, the total amount of energy is going up to plow that field, but the human energy goes down dramatically. Now, the last thing I want to highlight here, and these are where my numbers depart a little bit or fairly significantly from this original study right over here, this original estimate, is the machinery input on the tractors. So if you look this up, and you can Google search it, they have much larger numbers here, but I did a little research, and it looks like for most petroleum-based, combustion-based engines or vehicles, roughly 20% of the total energy that's used in fuel, 20% of that energy is used for the actual production and maintenance of that vehicle over its life. So what we did over here is we said, okay, for a 6 horsepower tractor, I used their numbers, where you're going to have to use 25 hours to do it. It's going to use this much petroleum, assuming that it uses 23.5 liters of gas or petroleum over 25 hours. And then I just took 20% of that number for saying, well, how much energy had to be used to maintain that vehicle over that amount of time. And if you think about what fraction of this vehicle's life that 25 hours represents, that fraction times the total amount of energy required to produce that. So remember, these things are made out of metal. They had to be made in furnaces. So just producing a vehicle requires a lot of energy. And so this right over here is 20%. And I just use that rule of thumb for most petroleum-based or combustion-based vehicles, the 20% of the total energy expenditure over the course of that vehicle's life is roughly equal to the amount of energy used to produce that vehicle. But either way, you go all the way over here, the human has to spend less calories sitting on the vehicle, so they spend less calories per day. And then the total human input right over here, for the 6 horsepower tractor, it's going to take them 2.5 days, 25 hours at 10 hours a day, is going to be 8,500 calories. But of course, you have the petroleum used and then some estimate of the amount of energy used to produce that tractor, and you're just taking the fraction over that 25 hours. You're not taking the entire life of that 6 horsepower tractor. To produce a 6 horsepower tractor, this number would be much, much larger if you talked about the total number of energy. We're just taking the small fraction of its life that we're using it right over here. Same thing for the 50 horsepower tractor. But any way you look at it, the human, and this is the really interesting thing, humans, by going from human power all the way to a 50 horsepower tractor, you're getting almost a factor of 200 improvement in terms of how little energy has to be put in by the human to till that land. But you actually get a total increase if you factor in things like the petroleum and then definitely the machine, the amount of energy to actually produce that machine. So anyway, hopefully you found that interesting. I find this, it's something that you don't think a lot about. How much energy input has to be put in, and oftentimes we only think about the human energy input, but we're not thinking about the energy input from other things like oxen.